Okay, so we're finished with the quadratics unit. We're going to move on to simplifying radicals unit. The radicals and exponents unit. So I just want to just talk about something. Maybe you know this. Maybe you don't need to take notes. I'm not testing you on this, but just something to know. So the idea is we're going to talk about this idea of square root. We say, what's the square root? And it literally means roots. When we say roots, I mean the sides of a square with area added. Once again, I'm not testing you on this, but you can take notes if you want. So we notice, so first of all, we know a square. What's a square? Well, you learned in geometry, it's a parallelogram. All the angles are congruent, and all the sides are congruent. They're all the same. Algebra equals geometry congruent. So the idea is, you have the shape, and there's all right angles, right? And, all the sides are congruent. And maybe I say to you, a side is 5 centimeters. So I say, what's the perimeter, and what is the area? Perimeter and area. And you say, oh, that's easy, Mr. Adler. Perimeter is the sum of the sides. And since you said it's a square and all the sides are congruent, we know it's 5 times 4, or 20 centimeters. And then I asked you to find the area. And you go, that's easy, Mr. Adler, because it's length times width, base times height, or side times side, 5 times 5. The area is 5 times 5, or 25 centimeters squared. Okay. How about if I tell you in the next example that the perimeter of the square is 40 centimeters? Well, what's the length of the side, and what's the area? And you say, okay, that's no big deal, Mr. Adler, because, well, just think about it. Okay, so you say, okay, well, hey, Mr. Adler, if all the sides are equal, I could write the equation 4s equals 40, and therefore one side equals 10. And if we just figured out that 10 is a side, I know that the area is 10 times 10, or 100 centimeters squared. Now, the last thing is, I might say to you, okay, if the area is 64 centimeters squared, find the side and the perimeter. And this is where this idea comes in. So you might say, so how are we going to figure that out? How are we going to figure that out? Well, you say, okay, well, we can set up an equation, right? We can set up an equation. We can say side times side, or side squared, equals 64. Okay, well, this is interesting. How do we undo a square root? You'll say, well, something times something equals 64. Well, and the idea is the s equals 8. So we say that 8 is the square root of 64. That's, once again, 8 is literally how you make a square whose area is 64, the square root. A couple of notation. So the idea is you might see, so the notation is, this is the notation for square root. You might see, or it's referred to the square, so this is the square root of 64. You might see radical 64. You might see the notation root 64. All of these are equal to 8, and that's the idea of the square root. Now, so I might ask you, right, I might say, okay, what is this? And you would say, oh, that's the square root of 100. Geometrically, I have a square whose area is 100, therefore the root of that is 10. Or you might say, maybe you've learned something times something equals 100. That's also 10. You might see this. What does this represent? I'm not using language. You see that symbol, those symbols. What is it representing? You might say, once again, there's a square with an area of 25, so the side is 5. Or algebraically, or arithmetic, 5 times 5 is 25, so the square root of 25 is 5. Now, that's all fine and dandy until I give you this. What's going on there? So you say, okay, well, I know what's going on there. So my question to you is, what does that mean? And you say, okay, that's the square root of 5. That means there's a rectangle, there's a square with an area of 5, and the side times the side equals 5. Well, that's kind of weird because we don't know that number. We know the perfect squares. We know 1 times 1 is 1, and 2 times 2 is 4, and 3 times 3 is 9, and 4 times 4 is 16, and so on and so forth. You should know all of them. But something times something equals 5? That's weird. My first question to you is, does this exist? Does this exist? Because if it doesn't exist, I don't even care about it. So, you say to me, hey, yeah, it definitely does exist, Mr. Eller. And I say, well, prove it. How do I know it? It's a number, right? The square root of this represented the number 10. And this thing represented the number 5. This thing represented the number 8. So what does that represent? And so what do you think? Okay, so your argument would be, hey, Mr. Adler, I know that radical 4 is 2, and I know that radical 9 is 3, so I know that radical 5 is somewhere between radical 4 and radical 5. And you might say, you know what? I know it's kind of closer to 4. It's on the number line. So this was your introduction to even filling up the number line even more. Positive numbers, negative numbers, fractions, repeating decimals. Let's see what's going on here. So you might say, okay, well, it's somewhere between 2 and 3, right? It's on the number line. Well, let's figure this out for a second. Let's get our calculators out. Because maybe we can figure this out. Maybe it's a nice decimal. It's a decimal. We're okay because we use our calculators now. So let's get our calculators and see what's going on. So how about 2.2 squared, right? Maybe this representation is 2.2. Right? And you say, okay, well, it's 4.84. Close. How about we try 2.3 squared? And check it in your calculator, and you get 5.29. Well, we know it's in there. We've zeroed in, right? How about we try a 2.23? And we get 4.9729. We're close. We're closing in there. How about a 2.236 squared? That gives us 4.9997. We're almost there. Are we almost there? Let's go at another decimal. How about 2.23606 squared? This would be it, right? How about 1, 2, 3, 4, 5 decimal places? We're definitely getting to 5, right? Well, we actually get to 4.99996. It turns out that this actually is the first 100 digits. Here's the first 100 digits of the square root of 5. I'll put it here on the board. You can pause it. These are the 100 digits. So the idea is that you learned about this. So radical 5, although it is between 2 and 3, it is irrational. And so we learned about this: radical 2, radical 3, radical 5, radical 7. These numbers, if you cannot get a perfect square under the radical, you're having these are known as rational. The decimals go on and on forever. Now, what we do is we use estimates. Use estimates. So radical, for example, radical 2 is approximately 1.414. Radical 3 is approximately 1.732. We're going to say that radical 5 is approximately 2.236. And another one, how about radical 10? Is approximately, my black pen ran out, let's use blue. Radical 10 is approximately 3.162. Well, that looks like another irrational number you've been studying over the years. Anyone? Yeah, it's pi. So it's a little bit less than pi, which is equal to 3.1415. So that's the idea of irrational. The decimals go on for we can't really get there, but so we approximate. Now, one last thing that you're totally not responsible. What is the idea behind it? So first of all, what is the difference? What is the difference? Between like radical 2, radical 3, radical 5, and pi, because they're both irrational numbers, but they look different and they're not the same. It turns out, this is kind of cool, and once again, you're totally not responsible. The idea is that the ancient Greeks actually were able to construct these, but they weren't able to make the distance of pi. And what did the Greeks do? You remember using those weird compasses in the sand? They actually so what they did was, they made one by one. They could make it one unit, and they made it perpendicular to a 1 unit, and when they connected this, that length is actually radical 2. They can make these lengths. So that's the difference between these irrationals and pi. You can make radical 3 by just putting a 1 here, and then connecting this. That's radical 3. You could just put a 1 here and just create radical 4. You can just put a 1 here and create radical 5. So you can create any single radical, and so you can make these lengths. You can construct it. This is what the ancient Greeks were trying to do. And so the idea is you can construct these. You can't construct pi. You just can't do it. So that's the difference. Kind of interesting. And so the last part that you are responsible for is, this is what you're responsible for, simplifying radicals. It shows up, it's something you should know how to do. Let's see. Oh, this pen's gone. Simplifying radicals. Simplifying radicals. And so the idea is you want to turn a larger radical into a simpler form. It's kind of like reducing fractions. So I'm going to give you a radical, and I'm going to tell you to simplify it. There's 2 rules. Remember that radical x times radical x equals, put that in your calculator. It turns out that radical x times radical x equals x, and the second rule you need to know is radical a times radical b equals radical a times b. Let's start with something basic. Radical 20. Radical 20 is between 4 and 5 because it's between radical 16 and radical 25. That's fine. But what I'm concerned is, how do I simplify this? It goes like this. Step 1, factor into primes. Make a factor tree of primes. So you go 2 times 10 and 5 times 2. Step 2, put radicals over the primes. So I see that, let's see, 5 is a prime, 2 is a prime, 2 is a prime. If you learn another method and you understand this, that's totally fine. This is just covers everything. Step 3, look for pairs. Look for pairs. So radical 2 times radical 2 is 2. Were we able to free the radical 5? No, it stays under the radical. Final answer, 2 radical 5. Let's try another one. How are we doing for time? Perfect. Let's try another one. Radical 12. Okay, next problem. Radical 12. Okay, step 1, a factor tree of primes. 2 and 6, 2 and 3. Step 2, put radicals over the primes. Step 3, look for pairs. 2 times 2 is 2. This 3 is still here. It stays under the radical. 2, radical 3. How about we try, and my favorite one, radical 48. I love radical 48. Let's look at 2 ways to do radical 48. You might say, 224, 212, 26, 23, right? And then put radicals over the primes. Radical, 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 radical. Look for pairs. A pair of 2s, 2. A pair of 2s, 2, 3. 4, radical 3. Now, some of you might say, hey, Mr. Adler, we learned something else, and let's talk about the other method. Other books say, look for the largest perfect square. So you might say, hey, Mr. Adler, 48 breaks down into 4 and 12, and 4 and 3. You might stop at the perfect squares. You know what? I'm putting radicals over those perfect squares. That's another technique. 2 times 2 times radical 3, 4 radical 3. It's up to you. But my method it's a surefire way. It works for everything. Radical 60. Radical 60. 2 times 30. 2 times 15. 3 times 5. Okay. Let's put radicals over the everything. 2 and 2, 2. What's going on with the 3 and 5? They don't have pairs. They go back together onto the radical. That's it. One last thing before we sign off. But now we're in 10th grade, right? We're in Algebra 2, so we have to take this up a notch. And it's very basic, same idea. How about I give you the square root of 45b cubed? Well, those aren't numbers, Mr. Adler. Well, they're variables and they still follow the same rules. Step 1, factor tree. I know I have 3, 3, 5, b, b, b. Right? Right? Put the radicals over the primes. Radical, 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 radical. Are there pairs? Oops. Are there pairs? Yeah. Radical 3 and radical 3, 3. B and B, B. Well, 5's alone and B is alone. It goes back onto the radical. That's it. And then this is the introduction to more advanced like exponents. You go, I might say, what's the square root of x to the 4th? And you go, okay, well, that's, x, 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 x. And so you have, actually it's x squared, right? Radical, 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 pair, pair. You might discover that x to the 10th equals x to the 5th, and an advanced 2, right? And we'll talk about it. You need to know this if you're going to take analysis. But it turns out that the square root of x can be written as x to the 1/2 power. Right? That's kind of interesting. A little advanced. Anyway, I gave you a worksheet and practice the radicals.